Good morning to all. In today's session, we will discuss about tree in data structure. So, what do you mean by data structure is, it is a place where we can organize and store the data. The data structure can be broadly classified into two types. Those are linear data structure and non-linear data structure. In linear data structure, we have some examples pointed out here: arrays, linked lists, stacks and queues. And in non-linear data structure, we have some types are highlighted here: trees and graphs. So, what is linear and non-linear basically means the data, the organization of data based on the arrangement of data, we are classifying the data structure as linear and non-linear. So, in linear case, we have given the pictorial representation of the various kind of data structure. So, first is the array data structure. In array data structure, the data elements are organized in a sequential manner. That is, when you look at the memory location, all the data are organized in a continuous memory location. This is what an array data structure. The next kind is the linked list. So, in linked list, this is also a kind of linear data structure where each elements are stored in a form of node. A node consisting of two parts, one is the data part and the another one is the address part. In the address part, the address of the next node carrying some data is linked with it. So, which carrying the address part carries the address of the next node which is connected with it. So, in this arrangement, here the nodes not have the continuous memory location. That is what the difference between array data structure and linked list data structure. So, in array, so all the nodes have the continuous memory location, but in linked list we do not have such restrictions. So, it is efficient. Then next kind is the stack data structure. So, this is a stack data structure. It follows the procedure of LIFO. What is LIFO means? Last in first out procedure. That is the element which is entered inside the structure last, which comes the first, which will be taken away from the stack structure as a first node. So, last in first out. So, next is the queue data structure. In queue data structure, here it is following the procedure of FIFO. What is FIFO means? First in first out procedure. So, here it is a real time example is like how we are maintaining a queue in a ticket counter. This is a real time example. Here the element which is the person who is entered in a queue first will leave off the first. Similarly, here the element which put inside the queue data structure will leave the first. So, we are having the two pointer in the structure, one is rear and front. So, similarly in stack structure also we are having two pointers, push and pop. Two operations called push and pop. Push means for inserting an element, pop means for taking an element. The pointer which is maintained in the stack data structure is called top pointer. Through this top pointer, the elements are pushed and are popped. So, this is the logic of the tree. So, what is tree basically? So, in this today's session we will discuss about the tree data structure. It is a kind of non-linear data structure. So, what is non-linear data structure means? In tree it's a non-linear data structure. Tree consisting of nodes, otherwise it is called entities, and these are organized in a form of hierarchical arrangement. See, look at this picture. Here some of the nodes are arranged in a hierarchical fashion. This structure is an example of a tree data structure. So, the first level here, some of the nodes are arranged in a level by level. So, level 0 and level 1, level 2. So, the topmost node is called root node, and some of the node are represented like leaf and some are represented as nodes. Let us see this example. So, here we will see what is children, what is sibling and leaf with this picture. So, this tree data structure consisting of, this is the root node. So, this root consisting of left subtree and this is called right subtree. These are the children of this root node. So, in this left subtree we are having some another level of child nodes are arranged here. This arrangement is called hierarchical arrangement. So, tree is a good example for hierarchical data structure. So, the last level node here, the node which does not have any more element further, that is called a leaf node. Some of the terminologies about this tree data structure are edges, depth and height. What do you mean by edges? So, when you have a tree structure, the number of nodes presented in this tree structure is n means, so number of edges presented in the tree structure is n minus 1. For example, if you have this tree structure, what do you mean by the edges, this is nothing but the edges, connector between the two nodes. This is what an edges. So here, how many number of nodes are there in this tree structure? So there are 11 nodes. So how many edges are there? N minus 1. So 11 minus 1, totally 10 edges are present in this tree data structure in order to connect all the nodes. So here these are the leaf nodes. So see this leaf node. This leaf nodes are the last level of node. Further that from the leaf node there won't be any child node. What do you mean by depth of some node x and what do you mean by height of some node x? So depth of the node is, we have to calculate the depth of the node from the root node. So here when you take this this node, so what is the depth of this node is from the root node, how many edges are there to connect the node with the, for example here only one node is there, so depth is 1. So for this node again we will calculate the height of that node. So height of the node is, so from that node to its longest path, how many edges are available? For example, this node having this path, so this the path 1 and the path 2. So which is the longest one? Both the path having the 2 edges, so its height is 2. In this way we will calculate each nodes and even the tree's height and depth also. So what is the height of the root node becomes the height of the tree usually. So here some of the applications of tree in computer science field is highlighted here. We'll create a file system with the help of this hierarchical tree structure, and we can create a dictionary, and Unix directory is also created with the help of with the logic of this tree data structure. Then in several networking routing algorithm have been used the concept of tree data structure, and binary search tree is one of the great implementation and example, real-time example of a tree data structure, where it will be used for searching a data item quickly, and we can insert and deletion of a data items also can be done very quickly with the help of this binary search tree. This is one of the kind of this tree data structure. Then the first, the basic, the first and important kind of a tree data structure, binary tree. What do I mean by binary tree? So in binary tree, each node can have at least at most 2 children. At most 2 children. So more than a node cannot have more than 2 children. So this is what a binary tree. So what is the difference between the normal tree and binary tree? When we see this example, this is a tree. When we take this node, so this node is having 3 children. Take this node, the node is having 3 children. It is a normal tree. But when you go for a binary tree structure, in a binary tree structure, see this tree structure, all the node can be having at most the maximum of 2 children only. So what are the possibilities of a binary tree? A node, how many number of children a node can have in a binary tree means, see here at most 2 children, a node can have only left or right child, or both the child can be available, or only one child is available, or no child is available. So these are the possibilities to create or to form a binary tree. So at the maximum of a node can be having only 2 children. Then these are the kinds of binary tree, strict or proper binary tree. In this case, each node having either 2 or 0 child. So either 2 child or 0 child. There won't be any possibility of having only single child in this. This is a difference here. So this is what a strict or proper binary tree. Then complete binary tree. It is another kind of tree data structure. So in complete binary tree, what is the property to be maintained here is the last level is completely filled. So look at this tree structure. Here the nodes are represented or arranged in a level by level. This is a root node, level 1. Then these are the 2 child node of this root. So these are arranged in level 2. Then this is level 3 node. This is level 4 node. So here, so look at all the levels are completely filled with the property of all the nodes are as left as possible, means left side node. In each level, left side node is completely filled. So in each level, left side is completely filled. This is what a complete binary tree. Then next, perfect binary tree. So in perfect binary tree, all the levels are completely filled. which means what is the difference between the previous case and this case? Complete binary tree and perfect binary tree means in complete binary tree, all the left child must be filled. But in perfect binary tree, all the levels, all the nodes must be filled completely. For example, in level 2, it is filled completely means it should be having both the left child and right child. So this is what the difference. Then implementation of binary tree. So we can able to implement the binary tree data structure in two methods or in two forms. First is dynamically created node, that is linked list, or by using array structure. So we can implement tree data structure in this two way. The first is dynamically created nodes, linked list structure. So in this structure, the node elements are arranged in this manner. Here this is a root node. The root node having the two portions, left child and right child. In its left portion, the left child's address is available. In the right side part, the right child address is placed here. In this arrangement is called linked list arrangement. So we are using linked list for implementing this tree data structure in this way. So this is a structure, a node, how a node looks like. What are the elements are available in each node. So in node, we are having data part, then left pointer and right pointer. So the left pointer is used to hold the address of the left child and the right pointer is used to hold the address of the right child. This is a node structure. In array implementation, it works only for complete binary tree. The array implementation of a tree can be done, or it will be applicable only for a complete binary tree. So in case of this is the pictorial representation of array implementation of a tree. So here the nodes and their child nodes are stored in some manner by following this property. Here for node at index I, so where its left child and right child should be placed. With the help of this formula, 2i plus 1 is used for storing its left child of the I, then 2i plus 2 is used to store the right side of the node I. So the node I, left and right childs are organized by using this formula. This is what an array implementation. Here some sequential arrangements is available. Then implementation of binary search tree. So what is called a binary search tree? It's another kind of binary tree. That is, here in binary search tree, what is the property is followed here is, look at this picture. So this is a root node, this is a left subtree and this is a right subtree. So in binary search tree, the key values are compared. So based on the key values of the node, the tree is organized. For example, so in left subtree, all the nodes in the left subtree, the key value is lesser value or equal to the root node, and all the right subtree nodes having the key value higher value than the root node. This is the property maintained for constructing a binary search tree. See, this is an example of binary search tree. See the root node, the key value is 25, and this is the left subtree of this root node and this is the right subtree of this root node. So in left subtree, so look at the nodes and its key value. All the nodes and its key value are having lesser value than the root node, and in the right subtree, look at the key values of the nodes in the right subtree of the root node. So all the nodes key value are having higher value than the root node. So this is a binary search tree construction. Then this is one real-time example of binary search tree implementation. Unix directory is made up of using the binary tree structure, data structure. Then the next we will discuss about binary tree traversal. What do you mean by tree traversal in the sense? So visiting all the nodes at least once in a tree. Visiting all the nodes in a tree to be visited at least once. This is what a tree traversal. So here the tree traversal can be performed in two manner. So one is breadth first or level order wise. Then second is the depth first method. In breadth first, in level by level, the nodes are visited. The nodes in a tree are visited in level by level, starting from the root node till the last level. The nodes are visited the level by level. For example, first we visit the root node, then we go for the next level nodes like D and J, then we go for the next level nodes like B, E, G, K. Then the next level node, the last level node. So level by level manner, the nodes are visited. That is what the breadth first order or level order. So here, this is the outcome of the breadth first tree traversal method. So what is it given here? FDJB. So F then DJ, then BEGK, then the last third level ACI, then the last level we have only one node H. So in the level by level we will visit the node. This is the outcome of the breadth first search. This is the first tree traversal method. Second tree traversal method is the depth first search. In depth first search we are having three types: pre-order traversal, in-order and post-order tree traversal. The first one, pre-order traversal. In pre-order traversal, this strategy is to be followed. For example, first visiting the root node, then go for left subtree, then go for right subtree elements. So in all the level, in all the left subtree or right subtree, the same procedure to be followed. For example, visiting the root element, then go look at the left child and go for the right child, visiting the right child. This order to be maintained in all the subtrees. For example, this is the procedure. This procedure is here recursive function call is applied, used here. For example, in this pre-order procedure, if the root node is null, we can return. So there won't be any nodes available anymore. If the root itself is null, just we can return. Then we can go for visiting the root node data. If the root node is there, go on visit the data. Then after visiting the root node data part, we will go for the left child. So pre-order root dot left. This is the recursive function call. Recursively, the same function is called for the left subtree, and after completing the left subtree, we will go for right subtree node. We have to visit the elements or nodes in the right subtree by calling this recursive function pre-order root dot right. So the example for pre-order traversal. So take this example picture, tree structure. So where the root node is F. Root node is F. Then from the root node F, after visiting root node F, we will go for left side node, left subtree. So the left subtree start with the node D. Here the node available in the left part of a root node F is D. So this itself having the left subtree, left tree and right child. Then we have to go back here for visiting its left child node B. Then B itself having left and right child. So we have to go again visiting the left node A. So after in this lowermost level, the bottom level of this subtree, in the left subtree B, see we have following the same procedure. So visiting the root node, then left child and right child. So in this case, B after A, after visiting A, we have to go back and we have to check whether is there any right child of the root node B is available. Yes, it is there. So we have to go on visit this node, C node also. So what is the procedures followed here? Visiting the root node, then left child node and the right child node. So here after visiting F, we have to go its left subtree. The left subtree which is having again a right child, a left child and right child. So we have to go left child again. So F, D, B, then A, C, then E. This is the way we have to traverse in the or following the pre-order. In the pre-order manner, we have to visit the nodes. In this tree traversal method, we have to visit the node in this manner. In the pre-order means data left and right, root node, left node and right node. So here in the after completing the left subtree, after visiting completely every node in the left subtree, we have to move on the right side subtree. In the right side subtree, look at the node J. The J itself having a left and right child. So what is the procedure to be followed here? We have to go for left node. So left node. After visiting G, again we have to go for left node, but there won't be any left node for node G. So we have to follow the right child I. After visiting the right child I, we have to go and check whether is there any left child are available. Left child is available. Yes, it is there. So go down and visit the node H. So after visiting H, go back and for J, there is a right subtree K, so that is also to be visited. So what is the steps are followed here? From J, G, I, H, then K. J, G, I, H, then K. So in all the level, all the subtree level, the same order to be maintained, the same procedure to be maintained. What is the procedure to be followed in pre-order traversal? Visiting the root node, then visiting the left subtree, then visiting the right subtree. Let us move on to the next kind of depth first tree traversal is the in-order tree traversal. In in-order, what is the procedure is followed here is left node, visiting the left node first, then come to the root node, then go for right child, right node. left, root, then right node. Visiting the left node, then root node, then the right node. This order to be followed in all the level, in all the subtrees. Here this is the procedure for in-order tree traversal. In this procedure again, we are starting our tree traversal with the root node. If the root itself is null, we can return back to the main function. So otherwise, we will go for visiting the left subtree. So by visiting the left subtree, what we are doing is we are calling the function in order root dot left. This function is called, this is a recursive function is called to visit all the left side node of the tree. After completing this, we go for root node. So root node is visited now, then that should be displayed here. Then after completely visiting the root node, we will go for the right subtree, and in the right subtree, we have to again apply the same principle for visiting all the nodes in the tree. This is the example tree structure for understanding or explain in order tree traversal. In this again, how we can start our procedure for visiting all the node in the in order manner. So in the in order, left, then root, then right. This is a principle to be followed. Left, root, and right. So here first we'll starting from the root node, we have to check whether any left child is there. Yes, it is there. Left child is available here. So we have to go just travel towards the left subtree. So in the left subtree again we have left node. Again we have left node. So till the last level left node, we have to come just visit one by one. So you have to reach up to the last level left side node. So in this subtree itself, we have to apply the same principle. For example, even reaching the node B, what we have to check whether there is any leftmost element is available or not. If it is, we have to go to that node, isn't it? So here A, after visiting A, left child node, then root node, then right child node. So A, B, C. This is the order to be followed here. In this way only we have to traverse in the in-order tree traversal. We have to follow the same procedure in the in-order tree traversal. So visiting the left node, then root node, then right node. So go back, then these all are getting visited, the all left node are visited. So go to the root node D, then go its right node E. So A, B, C, then D, E. A, B, C, then D, E is followed. So after visiting all the node in the left subtree, we have to go for the root node, F. F is its root. So after visiting all the node by using the in-order principle, we have to go to the root node F and visit this node that is available here. Then next is we have to move on the right side subtree of this root node. This is the right subtree. In the right subtree itself again we have to follow the same principle. What is the principle to be followed in the in-order tree traversal is left, root, then right. So here this is the root node. We have to check whether is there any left and right child is available. Yes, it is available. So go to the left. In the left node, we have to check whether is there any left node for this root is available. No, there won't be any left node for node G. So just go to the root node G and we go for the right child I. So G, then the right child, there is any left child. Yes, it is having, we are having the left child H. So G, then H, I, go back to the root node J, then go to the right child K. So this principle is followed in the right subtree. So in all the level, we have to follow the procedure, in order procedure. Next, the last type is the third type of depth first tree traversal is the post order tree traversal, post order. So what is post order means? After visiting left and right, we will go for the root. The root is visited at the last. That's why we will call it as a post order tree traversal. So if the root is visited first means pre-order, the root is visited at the middle is in order, if the root is visited at the last is post order tree traversal. Based upon the root element, at which time the root element is being visited, we are having this kind of classification. So here post order tree traversal, left subtree is visited, then right subtree is visited, then after that we will go for visiting the root element. This is the principle. So same, this is the function structure for post order tree traversal. So first root is, if root is null, then return, then post order of left, then post order of root dot right, then print the root data. Recursive function call is applied again in order to visit in all the level. So this is the example picture for post order tree traversal. So left, then right, then root. So here first we will visit all the elements of the left subtree first, then all the elements of right subtree second, then finally we will come to the root element. Here, searching an element in a binary search tree. So what I mean by binary search tree, already I told you in some other slide, no, binary search tree, the nodes are arranged depends upon the key values. All the elements in the left side having the lesser key value than the root node, then all the elements are organized in the right subtree having the higher key value than the root element. So we will take the example tree structure here in order to finding an element in a binary search tree. For example, the node highlighted here is 7. So we want to find this node 7. How we can start our searching? From the root node only we will start all our process. So here the searching process takes place from the root node. So in the root node, what is the key value? 12. What is the element to be searched is 7. So key value of element to be searched is 7. So the root node value is 12. So what we have to do is compare the element to be searched with compare the element's key value with the root node's key value. Here the root node is having the value higher than the element to be searched. So what we have to decide is we have to proceed further towards the left subtree. So if the key value to be searched is lesser than the root node, then we have to find or go for our searching in the left side. Suppose if the key value of the element to be searched is higher, for example 13, we take example is 13. If you want to search the element 13 means, so you have to check the element, the value, key value 13 with the root node key value. So 13 is higher, greater value than the root node value. So we have to go our search or start our search in the right subtree of the root node. So this is the principle to be followed in the binary search tree. Since being arranged, all the elements are arranged based upon the key value with the root element. So the searching takes place very easily. It will take very less time in binary search tree. Next we will look at the insertion operation of the in the binary search tree. So how we can able to insert a new element in a binary search tree? What is the principle to be followed here is, here actually how we are what principle we are following for searching or finding an element in a binary search tree. The same principle is applied in for inserting a new element in a binary search tree. For example, the element to be inserted is 13. For example, we take this is the key value of the element to be inserted. So in which here, so we have to check from the root node. The root node, when you comparing the element to be inserted, the key value with the root node, so it is greater value, higher value. So where we have to search, start our searching, we have to start towards the right subtree. The right subtree again we have to check the intermediate root node value with the element you want to inserted, 13 and 18. So 18 is again when compared to 13, 18 is greater value. So we have to go for left side, left subtree. We have to follow the left subtree. The element to be inserted having the less key value than the root node, we have to proceed further in the left subtree. So in the left subtree, it is having one more child. The node 18 is having the child node 15. So with this root node, we have to check our element for insertion. So 13 is having lesser key value than the root 15. So we have to find or fix the position only towards the left side of this 15. In the 15, we don't have any more element. It is left. It is left freely available. So we can insert the element 13 as a left child of the root 15. So step by step we have to follow the procedure. So first we will take element key value, proceed from the root node. Start from the root node. We have to check whether where we have to insert the element, where we have to find the position to fix the element. So we have, with the help of the key value, just we have to proceed further in the next level. Then deletion. How we can able to delete a node in a binary search tree. So we are having three types, three cases we are following for deletion operation, perform deletion operation in a binary search tree. The case one is a node which is to be deleted does not have any child. Then second case is a node to be deleted having only a single child. The third case is the node to be deleted having two child. These are the three cases we can follow, we are able to face while deleting an element from the binary search tree. The first case, the node to be deleted having no child. For example, in this picture we will take the element 8. We will take the element 8. So here it is a leaf node, there won't be any more child node from here. So this is the no child node. So here deletion of this leaf node is very simple. So we do not want to change the pointer positions. Simply we are not without disturbing the already arranged data structure. We are just simply deleting the element. Simply we are taking out the reference of this element. We are able to easily delete this element. The next case, deleting the node with one child. For example, 13. When you want to delete the 13, 13 is having one child node. So while deleting a 13, the node with one child, we have to make a proper arrangement for its child nodes. So where we want to link its child node. So that we have to consider. So when you want to delete the element 7, what happened? Here we have two more nodes, child node is here. So what is the principle to be followed? So when you are deleting the 7, some node from its child portions, child nodes have to replace in its place. For example, either 8 or 11 should come and replace in its position, so that we can able to properly maintain the tree data structure. Removing case 1, no child. Remove to reference of the node from its parent and return null. For example, in this tree data structure, we are going to delete the node 3. 3 is the leaf node, there won't be any child node is here. So simply deletion can be performed very easily. Just removing this node, just cut down this link, that's all. Removing this node from its parent node, that's all. We don't need to alter any of other data structure arrangements here. Case 2, deleting a node with one child. For example, you consider this right subtree. Here we are going to delete the node 13. So 13 is having one right child, 14, the value is 14. So right child is available here. How we are able to delete the node 13? What is the procedure to be followed? So this is a procedure. Find the node to be deleted, link its parent to this only child, remain attached to the tree. For example, it's for 13 having only one child, so no problem, just no worry about it. Just link this child node to its parent node. Link the child node of the node which is to be deleted to its parent node. So 13's parent node is 15. So simply we are going to cut down this edge, this link. We are going to delete the node 13. So simply you make a link from 15 to 14. That is what? Link the child node of the node to be deleted to its parent node. This is the principle to be followed in the deleting a node which is having one child. Case 3, a node which has two child, a node to be deleted having two child. We are having two methods. See, a node which want to be deleted having two child means, for example, in this picture 15. The node is 15. The 15 is having both the child, left child and right child. When you want to delete the node 15, what is the link to be given for its child node? So we are having two methods we can able to delete in this node. One is find the minimum in the right and copy the value in the targeted node, delete the duplicate from the right subtree. For example, finding the minimum in the right. For example, when you want to delete the node 15 means we are having two child. So we have to go to the right child and find the minimum value. For example, here in this example, the node 15 to be deleted, no? So here we are having only one node in the right side, 17. So no other node are available in its right subtree. So simply we will take 17 and make a link to its, we can copy the element value to the node which is to be deleted. So just replace the 15 by 17 and just to delete the duplicate element here. Just to cut down this link, cut down this edge, so that the 17 becomes here in this place. So this is the manner we can able to delete a element which is having two child, a node which is having two child in a binary search tree. So second method. Yes. Then case 3, finding maximum in a left side. For example, when you want to delete an element 15, the second method is, first method is finding minimum in the right side, then second method is finding maximum in the left side. So either we can go follow any of the method. So in this case, So in this second method, finding maximum in the left side. So here in the 15, where are the 15, the element 15 going to be deleted. So the 15 having two child node, 13 and 14. So among these two, which is the greatest value, maximum value? 14. The node 14 to be replaced in place of the node which is to be deleted here. So the 14 becomes in this place. So the 15 can be easily removed. So when you want to delete a node which is having two child node, we can follow either of the method. One is to find the minimum element in the right subtree and replace a node, or else find the maximum element in the left subtree and replace a node. This in any manner we can able to follow to delete the element which is having two children node in the binary search tree. Thank you.